Hello, welcome to the practical for the Zener Regulator. Here is the regulator here. We'll go through a quick explanation. I've just tripped the frigging thing, haven't I? So I keep it rolling. Come on, baby. You can do it. There we go. Okay, so what we've effectively got here is we've got a bridge rectifier. We've got an AC input to our bridge rectifier, and then we've got a smoothing capacitor here, and you can see that output of the bridge rectifier there with that ripple. If I remove the capacitor, or at least just unplug part of it, you'll see that the ripple disappears and we get that shape there on the bridge rectifier. So that's the effect the capacitor has on the bridge rectifier. It's quite profound. And on our schematic, basic schematic, this is the bridge rectifier with the AC input here. This is the smoothing capacitor here. And this is the regulator itself. And the first part of the regulator is where we have a Zener diode here, and that provides a steady switch-on voltage for this transistor here. And this transistor here is the thing that provides current across the electrical load and maintains a steady switch-on voltage. And we can see that in action. There's our Zener diode. This is the current limiting resistor for the Zener diode, and it's crucial because choosing this current limiting resistor makes sure we've got the correct operating current for the Zener diode. And there's our transistor. And this is the electrical load here. I've got three multimeters set up. They're all measuring current. This one here is measuring the collector current. This one is a Zener current, which should ideally be above 5 milliamps, and at the moment it's at 7.6. And this one here is measuring the base current, and the base current currently is at 5 microamps, and the collector current is at 6.39 milliamps. So, roughly speaking, the collector current, that's the current that flows down through the transistor here, is about 100 times bigger than the base current. And we'll see that as we change the electrical load, that relationship is roughly maintained. We can switch the electrical load here. This is the load. This is the Zener output voltage, the red line on the transistor there. And as I switch the load down, I've halved the load, and what's happened is the collector current has doubled. There's still a rough relationship of about 100, the collector current being 100 times larger than the base current, but we note that the Zener current has remained rather steady there. And we're going to take the load down further here. We note that at about 90 ohms, we still have the 5 volts DC there. And as I take the load further and further down, you'll note two things. The ripple voltage here becomes much deeper. That's because the capacitor is discharging into a much lower electrical load, so it discharges much faster. So in order to be able to do much more with this, we would need a larger cap. But we take the load down, and there we are at 50 ohms. We're still relatively steady here. Note the ripple voltage becoming much deeper still. There we are at 30 ohms, 20 ohms, and then when I go down to 10 ohms you'll see a profound difference, and you can definitely see the dip there. We could cue a part of that by using a much larger capacitor here. So if I put this capacitor in, note what's happened to the ripple here. So the capacitor is much larger capacity, and it therefore discharges slower. And I go down to 10 ohms this time. I do get some drop, but it's not quite as profound as before. And the capacitor helps to cure some of that. So that's effectively it. Just need to remember, voltage regulators, they maintain a steady output voltage across a range of electrical loads. So what I've been doing there is I've been adjusting this electrical load downwards, and we've been noting. Sorry about that. It's burning. Didn't quite switch it off enough. I better switch it all off, actually. Can you smell it?
Yeah.
Oh dear. Yeah, what we've been doing, we've been changing the electrical load downwards. We've been noting that as the electrical load halves, the collector current doubles, and the collector current has to double, the transistor current has to double in order to maintain a steady output voltage across this load. So it's a transistor which is able to change its internal resistance and provide more current to maintain a steady output voltage across the load. And that's all proved by Ohm's law here. The voltage across the load is equal to the current times the resistance. So to maintain an output voltage of 5 volts, if we have a collector current of 6.4 milliamps here, then we've got a load resistance of 780 ohms. If we half the load resistance effectively, then the circuit has to be able to provide double the current in order to maintain that relationship across the electrical load. That's it. Thanks very much, mate.